this is week 8 of the applied thermodynamics course problem solving session. So uh, in the previous weeks, so we have covered two types of cycle. So one was the vapor power cycle. So before that we also saw the Carnot cycle, how it works. Then we said how Carnot cycle is not practically possible, and we tried to incorporate it into a two-phase dome, and we tried doing a vapor power cycle. Then we shifted to a gas power cycle, and that too we saw some cycle having some similarities with the Carnot cycle, and we also did an exergy balance and analysis of this cycle to compare it with the Carnot cycle. In this week what we are doing is an extension to the Carnot gas power cycle. So here we'll look at a Brayton cycle. So to see that, we'll go first, we'll see what is a Brayton cycle. So Brayton cycle has four processes. If you see, these four processes are similar to what is there in a Rankine cycle. So we compare Rankine cycle with a Carnot cycle. So there we change the isothermal process to an isobaric process, saying that for a pure fluid, during phase change your pressure and temperature will be same, so you can replace one another. So that was the idea of putting a Carnot cycle inside the two-phase region and converting it to a Rankine cycle. And then we said the practical difficulties of having operating in a two-phase region, and then we try to take the process out of the two-phase zone. So that left us with four processes. One was compression, which was adiabatic, so isentropic compression, so reversible adiabatic compression. And then we had heat addition, which happened at constant pressure. Then we went with expansion, and then a constant pressure heat rejection. So these were the four processes which happened. So now in the Brayton cycle, the fourth process will remain same, but instead of having a phase change, now this is happening far away from the two-phase region. So this is happening at a gas phase or vapor phase, you can say. So superheated region. So the whole thing will be in gas phase. So this is the process. So previously this 1, 2, 3, 4, this is your Rankine cycle, and that is changed to A, B, C, D. So this is your Brayton cycle. So if you see, the process remains same. So the region in which you are operating has changed from the Brayton Rankine cycle. And this has also a similarity with your diesel cycle. If you see, diesel cycle, you had a constant volume, first a compression, and then constant pressure heat addition, and then you expanded and did a constant volume heat rejection. So in this case, Brayton cycle, the three processes remain same. The heat rejection now, instead of constant volume, you are expanding some more and you are rejecting heat at constant pressure. So there is also a slight similarity with your diesel cycle. So with this we have got an idea of how a Brayton cycle works. So we'll move on. So this is how the Brayton cycle looks in a PV diagram and a TS diagram. So 1 to 2 is your compression process, which is adiabatic, reversible adiabatic. So 1 to 2, then 2 to 3 is your constant pressure heat addition, then 3 to 4 is again expansion, which is happening at reversible adiabatic process, then 4 to 1 is your constant pressure heat rejection. Similarly, in a TS diagram, this is how it looks. So you have 1 to 2 and 3 to 4, which is reversible adiabatic, so your entropy will remain constant, and these two are isobar lines, so through which your heat addition and heat rejection takes place. So with this we can also derive for this process your efficiency formula, which is nothing but your work done, net work which developed, divided by the heat which is added. So on simplification, this is what we get, this is 1 minus 1 by Rp raised to power gamma minus 1 by gamma, or you can write Rp max is T max by T min raised to power gamma by gamma minus 1. This is your maximum which you can go. So now we will see what from this efficiency formula you can see that when your pressure ratio is increasing, your cycle efficiency increases. So that is one point which can keep in mind. So your pressure ratio is increasing, your cycle efficiency is increasing. But when your compression ratio increases, so your inlet temperature T2 which is happening, that also increase. So so there is a restriction from a metallurgical point of view. So you cannot exceed some temperature. So there is a limitation on maximum temperature which you can reach. So that limits your cycle. So that is one of the limitation in a practical aspect, so which you will have. So but when you compare with when you are defining this maximum temperature, so as shown in the figure here in the down left, so this is your maximum temperature which is fixed, and with this constraint, when you are changing your pressure ratios, so initially your cycle will look something like 1, 2, 3, 4. So this will be your cycle. So when you are increasing the cycle pressure ratios, so you will go from 1, 2 dash, 3 dash, 4 dash, 4 double dash, and when you are having a maximum compression ratio, so it will become 1, 2 dash, 3 dash, 4 dash. So with this we know that your efficiency will increase when your cycle is moving to the left. But if you see the area under the curve, so the area under the curve decreases when your pressure ratio is increasing or compression ratio is increasing. So when your net work done is low, what it says is compared to the first pressure ratio cycle 1, 2, 3, 4 and 1, 2 dash, 3 dash, 4 dash, you require a higher mass flow rate to get the same amount of work as generated using the lower compression ratio cycle. So when your mass flow rate is increasing, practically speaking, you require a bigger sized compressor, and other equipment sizes go up. So increasing your pressure ratio is increasing your component sizes. So capital point of view also, you have an increased cost out of this, going to a increased compression ratio, and also even though your efficiency is increasing, your net work produced is decreasing. So if you plot your net work done with respect to compression ratio, so this is how the cycle looks like, and you have some optimum where you have a maximum net work generated. So that optimum pressure ratio is given by T max by T min raised to power gamma by 2 gamma minus 1. So this is nothing but you write an expression for W net, which is your work done, work generated during expansion minus your work given in compression. And when you differentiate this with respect to pressure ratio, compression pressure ratio, which is P2 by P1, and you obtain the expression. So this is what you will get, which is T max by T min raised to power gamma by 2 gamma minus 1. So correspondingly, for this optimum pressure ratio, your net work generated is MACP into T max raised to power half minus T min raised to power half the whole square. So this is the net work corresponding to this optimum pressure ratio. So next is so if you see mostly this Brayton cycle, you have two types. One is an open type cycle and closed type. Generally what you will look at is the open type system. We can see in aircrafts and so on. So what happens basically there is you are compressing it, then you are adding heat, then you are expanding it, and you will leave it outside. Or if you want, you could put a regenerator and reduce the temperature by heating the inlet air, and then you dump it into the atmosphere. So that is an open type Brayton cycle. As we also saw the similar processes in Rankine cycle, so these are all employed to increase your efficiency and so on. So we'll look at this problem, how we saw how the efficiency was affected by employing intercooler, reheater and regenerator in Rankine cycle, and how it also improved our quality requirement at the exit of the turbine. So that was one of the constraints which was to be addressed. In this case, a Brayton cycle, a similar processes are also employed. So you have an intercooler in compressor, so to reduce the total work there, and also a reheater put in turbine to increase your net work, and also a regenerator which we saw similarly. So this here shown is a closed type. So after regenerator, you are rejecting heat and you are taking it back. But ideally you will use an open type where you are putting in air and then add it by combustion and then expand it, and you using a regenerator and you will dump it out. So that is an open type system. So with this we have a brief idea of how a Brayton cycle works, and we'll look at some of the problems of Brayton cycle. So starting with some multiple choice questions. So the first is, major applications of gas turbines is recognized for dash engines: A. aircraft engines, B. locomotive engines, C. automotive engines, D. all of the above. So this is a simpler one, so which I have already told, where Brayton cycle is used. So it's used in aircraft. So locomotives, your railways, and you use diesel or electrics, and then automotives, we know we are using diesel cycle and auto cycle, and nowadays mostly it's all electric. So but in automotive we are using diesel or auto cycle. So the answer is option A, aircrafts. Next is, reheating in a gas turbine cycle is employed to dash: A. increase the compressor work, B. decrease the compressor work, C. increase the turbine work, and D. decrease the turbine work. So if you see, reheating is done in case of turbine, and intercooling is done in case of compressor. So for this you do it in stages. So first answer for this is so we'll see how an reheating works in a turbine. So turbine, you have some gas which is at higher temperature and pressure, so you are expanding it, and after you are expanding it to some intermediate pressure, you are not expanding it fully. So instead of employing a single turbine, you are doing it in stages. So first you are expanding it to some intermediate pressure, then you will heat the fluid again to higher temperature, and then expand it again in a second stage or low pressure pressure stage turbine. So with employing this, if you see, if you are done it in a single stage turbine, your work generated which will be less compared to what you do it in a two stage employing a reheating. So this will the second stage will give you an additional amount of work because of reheating. So this will increase your turbine work. So for this, the answer is option C, increase the turbine work. Next question is, for same power output, the overall efficiency of a gas turbine engine is dash as compared to internal combustion engine. A. More. B. Less. C. Same as reciprocating engine. And D. One of the above, none of the above. So answer is option B, less. So we can see it from the efficiency formula also. So we can compare the efficiency of the Brayton cycle and your simpler one will be your Otto cycle. So using both, you can see estimate for a same output how much your efficiency is varying. So the specific power output for a simple gas turbine cycle is a function of only pressure ratio. Answer A, true. Option B, false. So this we have already seen the expression for the gas turbine cycle. So your Brayton cycle is termed simple gas turbine cycle. So we know the efficiency formula for the Brayton cycle, which is efficiency is given as 1 minus 1 by your pressure ratio, compression pressure ratio, Rp raised to power gamma minus 1 by gamma. So it's just a function of pressure ratio. Also, assuming your gamma value doesn't change, so this just becomes just a function of pressure ratio. We saw efficiency is just a function of pressure ratio, and if you see efficiency is given as W by Q. So Q depends upon your temperature. So this overall specific power output, so power output depends both on pressure ratio and the maximum cycle temperature. Or if you see the pressure ratio itself is defined by the maximum temperature for maximum power output, which we saw the curve. So answer is option B, false. Next is, the ideal location for placement of an intercooler in a two-stage gas turbine unit is dash. We have seen that your reheater comes in between stages of the turbines, and intercooler is used between the compressor stages to reduce the net work for the compressor. So higher temperature in, so that will increase the work done of the compressor. To reduce that, you cool the temperature. So for that you use an intercooler. So this will be used between stages of compressor. So in between low pressure compressor and high pressure compressor. So option C. So moving on to the next question. The Brayton cycle which is employed in aircraft engine is dash. Option A, a closed cycle. option B, an open cycle. C, either closed or open cycle. D, none of these. So going back to the Brayton cycle, what is closed and cycle and open cycle? Closed is you are having the four processes, you are completing the four processes. You are compressing it, you are heating it, then expanding it, and then there is heat rejection, and the fluid goes back again in a cycle. In an open cycle, what happens is you take in some amount of air and or the charge, you are compressing it, you are doing a heat addition, then you are expanding it and you dump it to the atmosphere. Before dumping, you can use a regenerator, but eventually you dump it. The fluid doesn't go in the cycle, just like what we saw in a diesel engine or a compression engine or say a spark ignition engine. You are taking in air and you are having an exhaust. So similarly, in an open cycle, you are taking in some amount of air, you are going through this process, and instead of heat rejection, you are just dumping it, which is equivalent to doing heat rejection. So in aircrafts also, so this doesn't have a cycle, so this goes in open cycle. So in the wings which you have, so there you have the compressor, a turbine in between a combustion chamber. So this three constitute your compression, heat addition and expansion, and after expansion you just dump it out. So this goes to an open cycle. So answer is option B, an open cycle. So at optimum value of pressure ratio, the specific work output is maximum. Answer A, true, and option A is true and option B is false. So we saw how the specific work output varies with respect to the compression pressure ratio. So we plotted a curve, so it was like an inverted curve having a maxima. So basically it may not look like that, it will be a singular curve which have a maxima, and with the increasing pressure ratio, work done will reduce, but it may not be symmetric. So but the idea remains same. So at maximum work is obtained in the pressure ratio being optimum pressure ratio. So this pressure ratio optimum gives you the maximum. So answer is option A, true. So next is, with addition of a heat exchanger, there is dash in specific work output in a heat exchanger cycle as compared to idle Brayton cycle. So with addition of heat exchanger, they are talking about doing a regenerative cycle. So you are using part of the heat which is generated during the compression before sending it to heat addition. So if you are sending it a higher temperature, so it's well and good. You require very less amount of fuel to increase the temperature of the fluid or air before sending it to an expansion. So you are utilizing part of the energy which is going out waste, and you are recovering that. So the regenerator employs this idea. So this will with this, if you see, there is a change in efficiency because you have so employing a regenerator, what happens is you have two streams which is passing. One is the gas which is coming out of the expansion turbine is losing heat, and it is heating the incoming fluid which is going to the combustion chamber. So this is the process which is happening in the regenerator. So if you go back to the cycle, So this is what is happening. So this is your regenerator, marked regenerator. So the heat is transferred between, so compressor out is at 4, so this is heated to 5 before sending it to a combustion chamber where a heat is being added. So you are basically increasing the energy of the fuel. So from 4 it changes to 5, and for that you are employing the air which is coming out of the turbine, so 9 to 10. So with this what happens is the cycle is operating same, but your heat addition, the amount of heat which has to be added has gone down by employing a regenerator. So but your state 6 is remaining same and your 9 is remaining same, so there is no change in the states between the expanders. So turbine will operate between the same conditions with the regenerator or without regenerator. Only quantity is the amount of heat which is being added, so that is reduced by employing regenerator. So this will affect the efficiency, but the net work output which is you are getting is not changed because of this. So there will be change in efficiency but not the work output. So the answer is no change. So moving on, the next question is, a gas turbine plant operating on Brayton cycle has maximum and minimum temperature as 800 degrees Celsius and 30 degrees Celsius respectively. The cycle efficiency of the plant for maximum specific output is dash. So the maximum and minimum temperature is given. For maximum specific output is, so we need to find out the R optimum. So R optimum is nothing but, if you go back, which is T max by T min raised to power gamma minus 1 by 2 gamma. So that is RP optimum, and for this conditions your RP efficiency is 1 minus 1 by RP raised to power gamma minus 1 by gamma. So when you are substituting RP optimum in this formula, it will reduce to 1 minus root of T min by T max. So substituting the minimum and maximum temperature given, you have to substitute in terms of Kelvin. So 30 plus 273 will be 303, and that is 1073. So your maximum efficiency, so your efficiency corresponding to your maximum specific specific output, your pressure, where your net work is maximum. So your efficiency corresponding to your maximum specific work output is 0.47. So this need not be the maximum efficiency. So if your pressure ratio increases further, your efficiency will increase, but this is corresponding to your maximum specific work output. So that is 47%. Next is multi-stage compression with intercooling and multi-stage expansion with reheating in a gas power plant is intended for improving the cycle efficiency. So employing a multi-stage compression with intercooling and multi-stage expansion in gas plant need not improve the cycle efficiency. So answer is option B, false. A gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. So the gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the temperature turbine inlet. So utilizing the air standard assumptions, determine the gas temperature at the exit of the compressor and the turbine, the back work ratio, and the thermal efficiency. So we have now moved to numerical. So we'll see how to solve this problem. So what is all given is we are operating in an idle Brayton cycle. So this is how the Brayton cycle will look in a TS diagram. So 1 to 2 is your universal adiabatic compression, and then constant pressure heat addition. Then 3 to 4 is your isentropic expansion, and then 4 to 1 is again isobaric heat rejection. So with this, the cycle is operating in a with a compression ratio, pressure ratio of 8, and then your gas temperature to the compressor, that is the minimum temperature, is 300 Kelvin, and the maximum temperature, which is the temperature to the inlet of the turbine, is 1300 Kelvin. So what are we asked to find out is the gas temperature at the exit of the turbine and the compressor, which is temperature at state 2 and 4. So 1 and 3 is known. 1 is the minimum temperature inlet to the compressor, which is 300, and 3 is your inlet to the turbine, which is the maximum temperature 1300. So we need to find out the other two temperature points, state points, and the back work ratio. So back work ratio is the ratio which is utilized in the compressor. The thermal efficiency. So we'll see how to solve this one by one. So first is the air temperature at the compressor and turbine exit are determined from isentropic relation. So we know in compressor and expansion are taking place isentropically. So your entropy will be constant. So we are making air standard assumption. So we have used an air standard table for solving this. So for temperature T1, which is 300 Kelvin, your enthalpy corresponding to that temperature is 300.19 kilojoule per kg. So your pressure ratio is given as 8. So correspondingly to the rated pressure ratio PR2, with this will be same. So that will come out to be 11.09, and corresponding to that pressure ratio and the entropy, your temperature T2 will be 540 Kelvin, and the corresponding enthalpy at state 2 is 544.35 kilojoule per kg. So similarly, same process for an process T3 to 4. So T2 will be 1300 Kelvin, and corresponding enthalpy is 1395.97, and similarly you can follow an isentropic line, and or PR3 you can find out PR4, which is 41.36. So corresponding T4 is 770 Kelvin at turbine exit. So your back work ratio is for that we need to find out the work done in the compressor and in the turbine. So compressor work will be H2 minus H1. compressor work, which will be H2 minus H1, and turbine work is H3 minus H4. So from the figure you can find out the turbine is 2 1 and turbine work is 3 4. So the corresponding compressor work is 244.16 kilojoule per kg, and turbine work is 606.6 kilojoule per kg. So back work ratio is nothing but the ratio of the work utilized in compression divided by the work generated in the turbine. So 0.403. So that says that 40% of what work you are generating is being utilized in compression. So it's consumed by the cycle itself. So that is 40.3% of the turbine work output is used just to drive the compressor. So the thermal efficiency of the cycle is the ratio of the net work power output to the total heat input. So we see total heat input is H3 minus H2. So that is the heat addition process. So that comes out to be 851.62 kilojoule per kg, and your net work is the difference between the work generated in the turbine minus the work consumed in the compressor. So that comes out to be 362.4 kilojoule per kg. So substituting here, the thermal efficiency will be W net by Q in, which is 42.6%. So you can also find it using 1 minus Q out by Q in. So Q out will be H4 minus H1. So it will be 489.2 kilojoule per kg, and inlet is 851.62. So if we substitute, you will again get the same value of 42.6%. So next is, instead of having a idle cycle, so your turbine compressor comes up with the efficiency. So it will not be truly reversible adiabatic process. So this is how the process will look. So instead of 1 to 2s, it's in a reversible adiabatic process. You will have an entropy generation. So you will have process 1 to 2a, and similarly instead of 3 to 4s, you will have 3 to 4a. So what is given is, assume a compressor efficiency of 80% and a turbine efficiency of 85%. Determine the back work ratio, the thermal efficiency, and the turbine exit temperature of the gas turbine cycle discussed in the previous problem. So previously in the previous problem we have already calculated the compressor work. So your compressor efficiency is nothing but your ideal work divided by the actual work, and your turbine efficiency is actual by ideal. So with this you can find out the actual compressor work, which is your ideal compressor, which you have found at 244.16 divided by compressor efficiency of 0.8. So this comes out to be 305.2 kilojoule per kg, and your turbine output is your turbine efficiency into the actual ideal turbine efficiency into ideal turbine work. So 0.85 into 606.6, which we found out. So this comes out to be 515.61 kilojoule per kg. So with this two, now the new back work ratio will come out to be 0.592, so 59.2%. So previously it was 40.3%, but also the turbine work was higher. Here the turbine work has gone down, and you are utilizing 59.2% of the work in compression. So this is because of the irreversibility which is happening in the compression and expansion process. So next is we need to find out the thermal efficiency and the exit temperatures. So again with this we can find out actual enthalpy. So previously we know the inlet enthalpy H1, and now we have found out the compressor work. So adding those, which will give you the exit temperature enthalpy, which is 605.39 kilojoule per kg. So with this corresponding to this condition and the pressures, so your temperature is 598 Kelvin, and similarly we can find out heat added with this condition. So Q in H3 minus H2A, which comes out to be 790.58 kilojoule per kg. So previously it was 851.62. Here because of the irreversibility in compression, so you have much more energy here which is put in the fluid, so that causes a reduction in heat added, so 790.58 kilojoule. So the net work can find out with the work estimated with the efficiencies of the turbine and compressor. So the net work will come out to be 210.41 kilojoule per kg. So previously, if you see, the net work was 362.4, so that has dropped to 210.41 kilojoule per kg because of the irreversibility and the efficiency of the turbines and compressor. So with this, the efficiency is now W net by Q in, which is 210.41 divided by 790.58, which comes out to be 26.6%. So if you see, previously it was 42.6%, now it is slightly more than half, so 26.6%. So this this because of the irreversibility occurring within the turbine and compressor, the thermal efficiency has dropped from 42.6% to 26.6%. So this shows how sensitive the performance of the gas turbine plant is to the efficiency of compressor and turbine. So the gas turbine efficiency did not reach counted value unless these turbines and compressor are made much more efficient. So the air turbine temperature of at the turbine exit is determined from an energy balance of the turbine. So similarly, what we did in compressor, we can find out for the turbine out, can find out H4A, which is H3 minus turbine work, which comes out to 880.36 kilojoule per kg, and similarly T4A is 853 Kelvin. So determine the thermal efficiency of the gas turbine described in previous problem. If a regenerator having an effectiveness of 80% is installed. So you have already seen, so this is how an open type cycle looks with a regenerator. So one is your inlet, you are compressing it, and the compression out is 2A, so that is getting heated by the fluid which is outgoing. So the compressor out fluid 2 is heated to 5 in a regenerator, and in the combustion chamber you are increasing the energy to state 3, and then you are expanding it by producing work, and then that is at state 4A, which is used to heat the incoming fluid to the combustion chamber. So that goes back, is left out at state 6. So state 6 will be somewhere here, which is not plotted. So here the regenerator effectiveness is given as 80%. So it will be H5 minus H2A. So H5 minus H2A divided by H4A minus H2A. So that is Q by Q max. So maximum which you can go is the difference between the maximum temperature difference. So inlet of the cold and the inlet of the hot. So H4A minus H2A is the maximum Q max, and actual is H4A minus H6 or H5 minus H2A. So here H5 minus H2A divided by H4A minus H2A, and effectiveness is 0.8. In this we can find out H5. So H5 is 825.37 kilojoule per kg. So thus heat addition is, we know H3, which we have calculated previously. So 1395.97 minus H5 is 825.37. So this comes out to be 570.6 kilojoule per kg. So if you see the previous problem, Q in is 790.58 kilojoule per kg. Now using a regenerator from 790.58, the new Q in is 570.260. So close to 220 kilojoule per kg of heat is reduced because of employing a regenerator. So this adding of regenerator does not change the work output. So if you see, the process 3 to 4A still remains the same. So only thing which has changed is the amount of heat which is added and the amount of heat which is rejected. So you are employing the heat which is rejected, which previously the air is dumped out at state 4a, which is at higher temperature, and you have much more energy of the uh, air which is going out at state 4. So now we are using that, employing that energy in heating the fluid which is coming in. So that is changing the heat added. So with this efficiency, if you see the new efficiency is W net by Q in is 210.41 divided by 570.6. This comes out to be 36.9. So if you see, the ideal efficiency was 42.6. Then employing the efficiency of the turbine, it reduced to 26.6, and it has increased now using a regenerator to 36.9. So if you see, the thermal efficiency of the gas turbine has gone up from 26.6 to 36.9% as a result of installing a regenerator. So that helps to recuperate some of the thermal energy of the exhaust gases. So next is we will see how an reheater and intercooler affects the cycle. So this is how the cycle looks. So an ideal gas turbine cycle with 2 stages of compression and 2 stages of expansion has an overall pressure ratio of 8. So air enters at each stage of the compressor at 300 Kelvin and each stage of the turbine at 1300 Kelvin. So determine the back work ratio, the thermal efficiency of the gas turbine cycle, assuming no regenerator, and B, an ideal regenerator with 100% effectiveness. So this problem is of two parts. So one with regenerator and one is without regenerator, and this is similar. If you see, this problem is similar to what we solved in the previous problem. So your temperatures are same and pressure is also same, but instead of having a single stage, you are having a 2 stage. So we'll see what's happening within this. So for 2 stage compression and expansion, the work input is minimized and the work output is maximized when both stages of the compressor and turbine have the same pressure ratio. Thus P2 by P1 divided by equals P4 by P3 is root of 8, which is 2.83. So this also can be solved. So by minimizing the work done, if you solve, you will get P2 by P1 is root of the P4 by P1. So that comes out to be 2.83. So that is the pressure ratio between stages. So air enters each stage of the compressor at the same temperature, and each stage of the has the same isentropic efficiency of 100%. Thus at inlet, T1 equals T3, H1 equals H3, and T6 equals to T8 and H6 equal to H8. And similarly at exit, the enthalpy and temperatures are same in compressor and your turbine. So under these conditions, the work input to each stage of the compressor will be same, and so will the work output for each stage of the turbine. So first case, when there is no regenerator employed, so the back work ratio and thermal efficiency we have to calculate. So first is what is known to the inlet of the compressor. So temperature is 300 Kelvin. So corresponding enthalpy is 300.19 kJ per kg, so which is known, and PR value from the table is 1.386. So this we are using because your heat capacities are varying. To solve that, we are using this, or you can also solve it assuming your Cp is constant. So here we are employing the as and a table to solve this. So other ways, you assume your entropy is constant, and or you can do a Cp dt. Or you can solve it with the pressure ratios and the thermodynamic work calculation. So with this, PR1 is 1.386 and PR2 is P2 by P1 into PR1. So corresponding temperature at state 2 is 403.3 Kelvin for PR value of 3.92, and H2 will be 404.31 kilojoule per kg. And similarly, your inlet to turbine is known T6 1300 Kelvin, and corresponding enthalpy is 1395.97 kilojoule per kg. So your enthalpy out is 1053.33 kilojoule per kg, and temperature is 1006.4 Kelvin. So with this, we know compressor work in just twice of each compressor, because your enthalpies are all same, inlet and exit enthalpies are same. So 2 times H2 minus H1. So this comes out to be 208.24 kilojoule per kg, and the turbine out is 685.28 kilojoule per kg. So if you see in the first problem, when you had a single stage compressor and turbine, so compressor work is 244.16 and turbine out is 606.60, 244 and 606, 244 and 606. So here if you see, compressor work is 208, so the work has reduced using an intercooler, and turbine out is 685.8, so 644. So that is given increased in turbine efficiency. So net work, if there is an increase, it has come to 477.04 kilojoule per kg, and Q in is your primary heat added then and reheat. So from the cycle it will be H6 minus H4 and plus H8 minus H7. So that is the total heat which is added. So that comes out to be 1334.30 kilojoule per kg. So thus your back work ratio is compressor work in divided by turbine work out. So that comes out to be 0.304, and your efficiency is net work divided by Q in, so which is 477.04 divided by 133.4.3 kilojoule per kg. So this comes out to be 35.8. So if you see, compared to the previous one, when you had a single stage with no regenerator, the back work ratio is 40.3%, and your efficiency is 42.6. So now with having a two stage, the back work ratio has come down, which is 30.4. so you are having much more work output, but having this intercooler and reheater has not increased your efficiency, but it has decreased your efficiency. This is because of the reheat addition heat which is you are doing. So that addition is much more compared to what additional work you are generating out of it. So efficiency is 35.8. so there it was 42, so it has come down to 35.8 using the two stages. So having that, you are having a reduced efficiency. Also your initial capital cost is also going up, because we are now, instead of one, you are having two compressors and two turbines and intercooler and reheater and so on. So this is cost you more compared to the previous one, may cost you more. So comparison of these results with those obtained in the previous problem, which is single stage compression and expansion, reveals that multi-stage compression with intercooling and multi-stage expansion with reheating improve the back work ratio. So it drops from 40.3% to 30.4%, but reduces the thermal efficiency. So therefore intercooling and reheating are not recommended in gas turbine power plants unless they are accompanied by regeneration. So the addition of an idle regenerator, so which is having no pressure drop and 100% effectiveness. So if you see, this is one problem where you have reduced to 35.8% efficiency, assuming that your compressor and turbines are operating at 100% efficient. So if that efficiency is coming down, so this efficiency will further go down. So if you see in the previous problem in single stage, in your efficiency of the turbine and the compressor were around 80 and 85%, your whole cycle efficiency dropped from 42.6% to 26%. So here it's already at 35.8. so if your efficiency of now you have multiple compressors, you have two compressors and two turbines. So So each will have a different have efficiency. So that will cause even more drop in your efficiency. So the addition of an idle regenerator does not affect the compressor work and the turbine work. Therefore, the net work output and the back work ratio of an ideal gas turbine cycle are identical whether there is a regenerator or not. So your Q in for this case so if you are employing an regenerator, so you see your after compression, so your outlet is 4, so in regenerator it is going to 5 because it has a 100% efficiency. So your that will be given by 9 will come to 10. So your temperature out 5 will be equal to your hot in 9. So Q will be equal to Q max. So Q max is 4 minus 9. So enthalpy at state 5 will become 1053.33, and with this your new heat added is becomes 685.28 kilojoule per kg. So previously your heat added is 1334.3, so that has come down to your half of it, 685.28. So with this, when you if you see the new thermal efficiency, so this comes out to be 69.6%. So this is a drastic increase in your efficiency. So it is always advisable to have a reheater and intercooler only when you are using a regenerator. So regenerator increases your efficiency rapidly in this case. So note that the thermal efficiency almost doubles as a result of regeneration compared to the no regeneration case. So the overall effect of two-stage compression expansion with intercooling, reheating and regeneration on thermal efficiency is an increase of 63%. So as the number of compression and expansion stages increase, the cycle will approach the Ericsson cycle and thermal efficiency will approach Carnot efficiency of 76.9%. So if you see calculate Carnot efficiency, so for the maximum and minimum temperature of 1300 Kelvin and 300 Kelvin, so it will come out to be 76.9%. So that you can so this you can push it to multiple stages of intercooling and reheating with employing more than 2. So but that also has practical difficulties, but doing so you are converting that to an Ericsson cycle, which is will give you the same efficiency as Carnot cycle. So we see that is the cycle, how it will look like. This will convert into a constant temperature line, and here also heat constant temperature heat rejection and constant temperature heat addition. So that how it will look like, but it will have multiple stages there. So an industrial plant is equipped with a regenerative gas turbine as shown in figure. So the air inlet condition an industrial plant is equipped with a regenerative gas turbine cycle as shown in figure. The air inlet condition to the compressor are 101.325 kilopascal and 27 degrees Celsius. The compressor pressurizes air to 10 times the inlet pressure. So in addition, the maximum air temperature in the gas turbine is measured as 790 degrees Celsius. Also a temperature difference of 10 degrees Celsius is measured between the cold air stream leaving the regenerator and the hot air stream entering the regenerator. So the net mechanical power output is 106 kilowatt and the heat input source temperature is 2500 Kelvin. Also, the compressor and turbine operate with isentropic efficiencies of 87% and 85% respectively. So determine the heat rejection and addition rate for both the actual and ideal cycle. Determine the entropy generation rate in the combustion chamber. Find the exergy destruction rate in the combustion chamber and determine the energy and exergy efficiency of the cycle. So what is given, we will go one by one. So you have a plant with a regenerative gas turbine cycle. They are saying that inlet condition to the compressor is given, so 101.325 kilopascal, and which is 1 bar and 1 atmosphere and 300 Kelvin. The compressor is pressurizing to 10 times, the pressure ratio is 10. The maximum air temperature is given as 790 degrees Celsius. So 790 plus 273 will give you in Kelvin. They are saying a temperature difference of 10 degrees Celsius is measured between cold air stream leaving the regenerator and the hot air stream entering the regenerator. So your temperature difference there is given. So temperature to the hot end is given, you see. So that is of 10 degrees Celsius. And your net mechanical power output is given as 106 kilowatt, and heat input source temperature is given as 2500 Kelvin. So your isentropic efficiency is also given for both the compressor and the turbine. So we'll see how to solve this. So this is how the cycle is looking. So your inlet to the compressor, that is 1 atmosphere, 101.325 kilopascal and 27 degrees Celsius, and you are compressing it to pressure ratio of 10, and then you are passing it through a regenerator here, and here they are given that you are cold out, so that is your temperature 3, and your hot air stream entering. So hot air stream entering is your T5. So T3 minus T5 is 10 degrees Celsius is given, and then there you are doing a heat addition, so that is also given. Temperature source is 2500 Kelvin, and 106 is mechanical power output, net mechanical power, and you are expanding in the turbine, and so your maximum temperature is given. Inlet to the turbine is 790 degrees Celsius, and that's all is known. So this is how the process looks in a TS diagram. So this being an open cycle, so your exhaust is dumped at state 6, and also this is ideal process 1 to 2s and 4 to 5s, and the efficiency is given. So the actual cycle will look like 1, 2, 4, 5 and 6. So for the from the ideal cycle, the temperature at state 2 will be your this is an reversible adiabatic process. So T2 by T1 is pressure ratio raised to power gamma minus 1 by gamma. So T1 is 300 Kelvin and pressure ratio is 10, and gamma is 1.4. So substituting that, you will get the temperature at the exit of the compressor as 579.2 Kelvin, and the actual cycle T2 can be found as using an isentropic efficiency. So that is isentropic efficiency of compressor is ideal by actual. So this becomes T2 actual is T1 plus T2s minus T1 by your isentropic efficiency of the compressor. So this is nothing but you are writing in terms of enthalpy, assuming a Cp is constant, and so H is Cp delta T. So Cp gets cancelled, so we can write it in terms of temperature. So substituting this temperature, so T1 is 300 Kelvin inlet to the compressor. So T2s we have already found out 579.2, and efficiency of compressor is 87%. So substituting, you can find the temperature, the actual temperature at the exit of the compressor is 620.9 Kelvin. So similarly, the isentropic temperature at state 5 can be evaluated as, so if you see 5 is your exit to the turbine, so T5S is T4 into similarly 1 by pressure ratio per gamma minus 1. So your T4 is given 790 degrees Celsius, so 790 plus 273, which is 1063 Kelvin. So that comes out to be T5S as 550.6 Kelvin. So the actual temperature can be found out using the efficiency formula. So T5 is T4 minus the efficiency of the turbine into T4 minus T5S, that is your actual by ideal. So the actual will be ideal into efficiency of the turbine, and again it's expressed in terms of temperature. Assuming your Cp is constant, you get cancelled out, so you can express it in terms of temperature. So here T5 is 1063, T4 which is known, minus your turbine efficiency is given as 85%, so 0.85 into your inlet temperature 1063 minus your T5S, which you have found out ideal temperature out, is 550.6. so this gives you your actual temperature at the exit of the turbine is 627.4 Kelvin. So doing an energy balance across the regenerator, so if you see the regenerator is here, so inlet is 2, so m dot into 2 H2 minus H3 equals m dot into H5 minus H6. So rearranging, you will get m dot into H2, so it's just inlet stream minus equals the exit stream. So inlet is 2 and 5, exit is 3 and 6. So m dot 2 H2 plus m dot 3 H5 is m dot 3 H3 plus m dot 6 into H6. So your mass is all same, so there is no mass addition or rejection in anywhere across the cycle. So the mass gets cancelled out, and H can be written as Cp into T minus some reference temperature. So Cp also gets cancelled and reference temperature also cancelled. So it will become T2 minus T3 equals T6 minus T5. T2 minus T3 equals T6 minus T5. Here we know the difference between T3 and T5 as 10 degrees Celsius. So T3 equals T5 minus 10. So from this T3 becomes 617.4 Kelvin. So substituting this in the expression, so we can find out T6. So T6, the exit temperature T6. So now we know T3, we know T5, we know T6, we know T2. So T6 is T2 minus T3 plus T5, which comes out to be 631 Kelvin. So the net power output is known to be 106 kilowatt. So this can be used to find out the mass of the air circulation. So which is W net divided by the specific net work output. So net work is 106 kilowatt and specific work output is your difference here. So H4 minus H5 minus H2 minus H1. So that is, you can write in terms of CPT. So CP T4 minus T5 minus T2 minus T1. So CP assuming 1 kilojoule per kg Kelvin. So actually is 1.005. So here in 1 into T4 is 1063 minus T5, which we have calculated 627.4, and T2 620.9. Again we calculated it from the temperature on the compressor outlet, minus T1 is 300 Kelvin. So this comes out to be 0.9241 kg per second. So this is the max the mass flow rate. So if you see the ideal mass flow rate, assuming if it was 100% the turbine and compressor are 100% efficient, so the ideal mass flow rate will be instead of 5 and 2, it will be T5S and T2S. So substituting that, it will come out to be 0.455 kg per second. So if you again we can calculate the heat adder in the actual and ideal. So actual is H4 minus H3 and ideal also will be H4 minus H3, but your mass flow rate is different. So actual heat added will be mass of actual into Cp T4 minus T3, which comes out to be 413.8 kilowatt. So ideal one will be ideal mass flow rate into Cp T4 minus T3. So this will remain same. So just the mass flow rate is changing. So that causes the change in heat addition, which comes out to be 203.8 kilowatt. So the heat rejection rate can be evaluated as similarly. So heat rejection is you are going out at 6 and the ambient heat is 1. So the difference is m dot actual into H6 minus H1. So substituting that, we will get heat rejection as 307.4 kilowatt, and the ideal one comes out to be 149.7 kilowatt. So with that, we have found out the heat rejection and addition in both actual and ideal cycle. Next is determine the entropy generation rate in the combustion chamber. So we have to do an entropy balance across the combustion chamber. So this is how the entropy balance looks like. So in minus out. So combustion chamber is here. So S4 minus S3, so out minus in minus heat added because of, so minus Q divided by source temperature T into T naught, Q by T. So this will be equal to the generated S generated. So what is going out is m dot m dot into S4 minus what is coming in m dot into S3 minus Q added divided by the source temperature. So here your S4 is 6.376 kilojoule per kg Kelvin and P4 is 1013.25 kilopascal and T4 is 790 degrees Celsius. So we know this P and T, so corresponding is 6.376 Kelvin, and similarly at P3 we know the pressure and temperature. So P3 is 1013.25 kilopascal and T3 is 617.4 degrees Celsius. So for corresponding to this pressure and temperature, your entropy is 6.175. So substituting that, and heat actual is 413.8 kilowatt, and your source temperature is given as 2500 degrees Celsius. So substituting, your entropy generated is 0.02 kilowatt Kelvin. So with this, if you see the exergy destruction in the combustion chamber, so doing again an exergy destruction balance is your exergy in equals exergy out plus exergy destroy. So exergy in is m dot into exergy 3 plus Q added into 1 minus T naught by T source equals m dot into exergy 4, which is the outgoing stream, equals exergy destruction. So substituting this exergy in, it comes out to be 480 kilojoule per kg. So we know H3, we have calculated H3, H naught is 300.6 kilojoule per kg. The temperature corresponding to the ambient pressure and temperature, and S naught is 5.697, and X4 is H4 minus H naught minus T naught S4 minus S naught. So this comes out to be 615.8 kilojoule per kg. So substituting these values in exergy balance, you get exergy destroyed as 238 kilowatt. next is energy efficiency. So if you see, the actual efficiency of the cycle is the net work divided by Q added. So net work is 106 kilowatt, which is given in the problem, divided by the actual Q which is added, which is 413.8 kilowatt. So this comes out to be 25.6%. So the efficiency of the cycle is 25.6%. So if you see the actual efficiency, when the efficiencies of turbines are neglected, so it was 100% efficient. So in that case, the Q added is 203.8. So your efficiency in that case would have been 52%. So now it has dropped to 25.6%. So close to half of it, because of using a 85% turbine efficiency and 87% compressor efficiency has dropped your efficiency by half. Also your mass flow rate is also increasing because of the same work output which you have to generate. Next is to find out the exergy efficiency. So exergy efficiency is nothing but unit work divided by the ideal work which you have to give. So it will be QCC. So in case of a Carnot cycle, so Q added into 1 minus T naught by Ts. So this comes out to be 29.1%. So this basically says that if Carnot efficiency is 100%, so this is 29.1%. So comparing to Carnot efficiency is just 29%. Or in other ways to say, if Carnot generates 100 kilowatt of work, this cycle generates just 29.1 kilowatt of work. So that is what the exergy efficiency says. So with that, I have finished what I have prepared for today. So the main takeaway here was, in the Rankine cycle, using a reheat and all improved your cycle efficiency. May not generally improve, but the main idea of using a reheat there was to improve your quality at the exit of the turbine. So that too, you may find cases where you have a lower efficiency, or may not find a higher increase in efficiency. But doing so here actually dropped your efficiency, because the turbine and compressor are not fully 100% efficient actual case, and that dropped your efficiency of the cycle significantly, and that could be overcome employing a regenerator. So that is a bigger takeaway here. So regenerator plays a major role in a simple gas turbine cycle or a Brayton cycle. So that is one thing. Okay. with this, I finished the gas power cycles section, and so next week we'll see some problems on aircrafts, engines, and so on, and that would end the power cycles. So thanks for joining. Thank you. So I'll close my session.